Hey there, welcome back to Physics 371 Online. In our last episode, we finished by writing down the expression for the force that a magnetic field produces on three different kinds of currents, depending on whether we had a current in one dimension, a thin wire, or a current spread out over a sheet, which is characterized by a current per unit length, K, called the surface current density, or in a three-dimensional conductor, like a solid wire, where the current is spread out over an area, which we call the volume current density, J. And you remember that these three equations look very similar, except we're integrating over a different region of space. So for a wire, we integrate along a length. For a sheet of current, we integrate over an area. And for a volume that carries a current, we're integrating over a volume. But I, K, and J play the same role in these equations. So you'll have some occasion to use these formulas when you do calculations on the homework. Now, let's go on and talk about, before we move on to the next section, talk about a very simple relationship that we can derive that arises from the fact that charge is conserved. In classical physics, we found that there are three fundamental properties, three fundamental quantities that are conserved in all interactions given certain kinds of conditions. And of course, those are mechanical energy, momentum, and angular momentum. But charge is also conserved, and this is an absolute conservation law. I think I can say safely that there's no observation that we've ever made that has violated the conservation of charge in some kind of interaction in matter. So, for a 3D current in a conductor, we can write down the total current that passes through a particular surface area in this way. This is just turning around the definition of J. If you'll remember from a previous slide, J was defined as dI divided by dA perpendicular. So if we just turn that around and solve for I, we would see that dI is J dot dA. And so if we integrate J dot dA, we get the total amount of current. And this is a flux integral. You'll recognize this from something like Gauss's law, where we were calculating the flux of field lines. Here we're calculating the flux of the current density, which is actually dimensionally the current. Now, the total current then that leaves a particular volume. So let's imagine now that this area is not just a plane in space, but we're thinking of, let's say, a sphere that's bounded by a closed volume, or a closed surface. So the current that leaves a volume through that surface can be written like this. It's the flux of J, written down as the integral of J dot dA over a closed surface. And we know, according to the divergence theorem, that that has to be equal to the integral of the divergence of J. So remember that the integral of the derivative of a vector function is equal to the surface area, the surface integral of that same quantity. And so this kind of relationship, no matter what J is, will always hold true. But we see that this term on the left-hand side represents the net current flowing through this region. And so now here's the point. If charge is conserved, then current, since current is a flow of charge, the current that leaves this closed surface, the current, in other words, that leaves this volume, has to be compensated by a reduction of what's inside the volume, right? So, if we can't have charge building up in some place or being removed from some place, and so the only way for this to work out is if this flux of current then is equal to the time rate of change of the charge that's inside the volume, right? These are just two different ways of writing the same thing. On the left-hand side, we have the flow of charge out, and on the right-hand side, we have the rate of change of the charge that's inside, right? If charge inside is leaving, then that's what the current represents. And the minus sign, of course, is there because the charge that's inside that region must be going down if it's flowing out. And then with just a little bit of manipulation, we can see rho, of course, being a charge per unit volume, could be a function of x, y, and z. And so we will write this derivative as the partial of rho with respect to time. And then one final last step, we can look at these two volume integrals, and on the left-hand side, and then on the right-hand side, and realize that if those are always going to be true, then the integrands themselves have to always be true. And so we get what's called in electrostatics, or in magnetostatics, we get what's called the continuity condition. Del dot J, the divergence of J, is equal to the time rate of change of the charge density. So that's simply a mathematical statement of the conservation of charge. We may not use it too much in this course, but you will run into it at some point in the future if you continue your study of electrodynamics. Now let's move on to talk about the origin of magnetic fields, and we'll introduce something that you ran into in your intro physics course that's called the Biot-Savart law. Thus far, if you think about what we've done, we've assumed that we can create a magnetic field, and we've examined what that magnetic field does to moving charges and the force that it exerts on currents. And so that's helpful because it tells us, if we know there's a magnetic field, what it's going to do to things. But how is a magnetic field produced? Where does it come from in the first place? And Ørsted, as far as we know from the accounts at the time, discovered quite by accident that an electric current caused the deflection of a compass needle. And so with some intense experimental work, he, along with French scientists Jean-Baptiste Biot and Félix Savart, along with help from Andreas Ampere, figured out a quantitative relationship between the current in the wire and the magnetic field that it produces. And of course, what we're going to look at now is a little bit of a modern account of what they discovered, because they probably used very different notation. But if we look at the picture, what we see is a current carrying wire and then a point over here in space, P1, where we would like to find the magnetic field. And it's defined with respect to an element of current here, which is written down as I times dl. Right? There's an element of current right here at the origin, and the magnetic field, the element of magnetic field dB that it produces at point P1, is given by a vector integral. And this, of course, is why, in order to study the physics of electricity and magnetism, we have to know vector calculus. We have to know how to integrate and differentiate vector quantities. Well, let's unpack this expression a little bit, but first of all, what we see is that there is a proportionality between the magnetic field and the current that produces the magnetic field. And all the rest of what's in here, mu naught over 4 pi, is a proportionality constant, and then dl cross script r hat, by the way, in the equation, script r is indeed the vector that goes from the current element to the point P1. I grabbed this diagram from a book that wrote it as just a regular printed R, but that actually, according to our textbook author, should be written as the vector script R. And so there's a proportionality between this cross product, dl cross r hat, and it's divided by the distance r squared. And you can think of this equation, which is the Biot-Savart law, as the magnetic equivalent of Coulomb's law. It has the familiar 1 over r squared dependence, and it shows, indeed, that magnetic fields come from currents. Now, it's more complicated than Coulomb's law because of the presence of this cross product. If we go back and look at Coulomb's law, it tells us how E depends on Q. And there's just a simple r hat unit vector in that expression. But in this one, there is this cross product. And if you remember your cross products, this shows you how to calculate, using the right-hand rule, the direction of the magnetic field that a current produces at a point in space. So you can verify yourself that the cross product of dl and this r vector is indeed pointing downward, as the sketch shows for dB. So we'll show how to use this in a minute. Mu naught, by the way, is called the permeability of free space, and it has the value 4 pi times 10 to the minus 7 Tesla meters per ampere. Magnetic field in our common SI system of units is measured in units called Tesla. This quantity in the integrand can be thought of, just as the sketch shows, as the differential amount of magnetic field that's produced by this differential amount of current, IDL. So, another way that this can be written, if we want to use the current as the vector quantity, then we can write this totally equivalently as mu naught over 4 pi times the integral of I cross r hat dl over r squared. It's just a matter of preference whether you would like the vector quantity to be the dl, which is the length element of the wire, or whether you would want it to be the current. dl is always along the direction of the current, which is why these two are equivalent. And again, just to remind you, I'm not a French speaker, but I've been told and I believe that the proper way, or at least a somewhat more proper way than we as English speakers might think, of pronouncing this law is the Biot-Savart. The T's are silent. Here's a simple example of how to apply the Biot-Savart law to do a simple, very simple calculation. If we have a circular ring of wire of radius r, what will be the magnetic field at the center? So there's a current I going around this wire, and what we need to do is take the Biot-Savart law, which has this dl cross r hat in the numerator, and evaluate it. So we pick a point. Right here it's indicated at the top of the ring, and let's assume the current is flowing in this counterclockwise way. So dl points in the z direction. The r hat vector, script r hat, always points from the current toward the point where we're trying to find the field. And one of the nice things about simple shapes like circles is that the dl vector and the r hat vector, wherever you are on the ring, will always be 90 degrees apart. So the magnitude of dl cross r hat is just dl, right, times 1, because r hat is a unit vector, times the sine of 90, which is also 1. And some simple inspection will show, through the right-hand rule, that dl cross r hat, no matter where you are in the circle, will always point in the x direction. So we'll call it I hat. And what's left then is just dl I hat. So that complicated-looking cross product that's in the Biot-Savart law reduces to something really simple. So now we go back to the Biot-Savart law. Mu naught I over 4 pi times the integral. It was dl cross r hat. It becomes dli. And the denominator, remember, was script r squared. Well, the script r vector always points from the wire toward the center, because that's where we're trying to find the field. And that distance will always be the radius of the ring. So that becomes r squared, and then everything can come outside the integral except for the dl. And what's left behind, even though it looks like an integral, is something that's simply a matter of geometry. The integral of the dl distance all the way around the loop is nothing more than the circumference of the loop, 2 pi r. We put the I hat in there to indicate that the magnetic field is always in that direction here. So the simple result that we get is that for this circular ring at the center, the magnetic field is mu naught I over twice the radius. Now, it's sometimes useful to try to calculate an expression for the magnetic field at some general point on the axis of the ring. So at some distance x away from the center of the ring, what would be the magnetic field? The Biot-Savart law can be used to do that too, but it's a little more complicated, and I'll let you look at that in the textbook. Let's look at a harder example than the circular ring. And this one I'll just drag you through very briefly. It's done also in the textbook in a very similar fashion to this. But it's a harder example because there's a lot more geometry to deal with. So here's the question. Find the magnetic field along a direction perpendicular to a straight current carrying wire. So here's my straight wire, and I've just grabbed a figure from a book that shows that it begins at a position x1 and ends at a coordinate x2 along the x direction. The y direction is perpendicular to that, and so what we want to do is find the magnetic field at point P, which is a distance r away from the line that goes through the wire. So this will only work for a straight wire. The result that we're going to derive, it assumes that we have a straight wire. And what we can do once we get the general result is we can put in limits so that we will obtain the result for a very, very long wire as kind of a special case. And that's often a useful thing to know. So let's go ahead, jump right into it with the Biot-Savart law. Once again, we have to label these vectors if we want to simplify Biot-Savart. So here is our element of current right here, and it's pointing in the positive x direction, and that's dl. The author did not draw the dl vector on top of the wire because it would be hard to see. So he drew dl as having an infinitesimal magnitude dx, because it lies along the x direction, and it's in the x direction, so dl is equivalent to dx I hat. X, of course, labels the position of that current element with respect to the origin. And then the r hat vector goes from the current element to the point P. Well, more correctly, the r hat vector points in that direction. The script r vector is the vector from the current element to the point P. And so the angle between those two is the angle phi. Remember, dl points in the positive x direction, r points toward P, so the angle between them is this angle phi. All right, so dl cross r hat is dl times 1 times the sine of phi. And what's the direction? Well, according to the right-hand rule, we see that the direction is out of the page. And in this coordinate system that I've chosen, where x is to the right and y is up, out of the page is z. So k hat is the unit vector that we use for this. Okay, so that simplifies the numerator. So now Biot-Savart becomes b equals mu naught I over 4 pi integral of dx sine phi over script r squared times k hat. I realize here that I'm using, in this example, k hat instead of z hat, but I hope you'll be able to understand what I'm doing. So now what do? Look at this integrand. What's really confusing about it is it's actually got 3 variables in it. Because if we move along the length of the wire, if this dl is at different locations, we're eventually going to want to integrate along the length of the wire. And if we do that, then there are 3 things in the integrand that are changing. The value of x is changing, the angle phi is changing, and the distance script r is changing. So we've got this ill-defined integral, and in order to actually evaluate it, we have to convert all those variables into just one single variable. And which one's easiest, it's hard to say ahead of time, but I will follow Griffiths and you'll get the same answer, no matter which variable you convert the integrand into, but I will follow Griffiths and convert it into an integral involving actually a different variable, theta. And so theta is the angle that goes from the y-axis to the line that joins point P and the current element. All right, so theta is the angle that goes from here out to here, and that specifies the location of this current element. And theta 1 would give the location of the left end of the wire. Theta 2 would give the location of the right end of the wire with respect to point P. Okay, so that's what I'm going to do. So we can see that the sine of phi is actually related to the sine of theta. There's a right triangle here that has theta as the upper angle, and so the angle down here is 90 minus theta, and phi is related to 90 minus theta. Phi, in fact, is equal to 180 minus theta, because 90 minus theta plus phi has to equal 180. So phi is equal to pi minus theta, right? And so, wait, is that right? Let me think about it for a second here. Okay, this angle, as I said before, is 90 minus theta, or pi over 2 minus theta, which is pi minus phi. So pi over 2 minus theta equals pi minus phi. So theta equals pi over 2 plus phi. Okay, all right, so that gives us the relationship between them. So phi here and pi minus phi just happen to have the same sine value, right? The sine of phi is equal to the sine of pi minus phi. And that's just a relationship that you can verify using any trigonometry book. And what we find is, here's the angle pi minus phi. That's equal to theta, 90 minus theta. And the cosine of theta is equal to the sine of pi minus phi. So this is how we transform the integrand from depending on phi to depending on theta. We'll replace the sine of phi with the cosine of theta. So that means we can also look at the triangle, this right triangle, and realize that the cosine of theta would be the adjacent side, capital R, over the hypotenuse, script R. And so then R cosine theta is equal to capital R, which means that script R is R over cos theta. And that's going to be important because that's in the denominator. So we have an expression for sine phi. We have an expression for script R. Now we need an expression for dx. And to do that, we need the relationship between x and theta. And that's pretty easy, right? Tan theta is x over capital R. And so x is equal to capital R tan theta. And if we differentiate both sides, we see that dx d theta is going to equal r secant squared theta. Or, taking that apart, dx is equal to r secant squared theta d theta. And secant squared is the same as 1 over cosine squared. So, now, on the next page, what we're going to do is take the Biot-Savart law and substitute in for dx, for sine phi, and for script r squared. And then we'll be ready to evaluate it. We're very close to the end. So, finishing off, there's our expression for Biot-Savart. dx, we said, had the value r d theta over cos squared theta. That's dx. Sine phi was cos theta. And finally, script r was r over cos theta, and so script r squared is r squared over cos squared theta. So what happens here? Take a look. Well, we end up with the r's canceling out. Actually, one of them does, because we have r over r squared. So that'll pull a factor of r outside the integral, and we've got cosine squared. The cosine squareds in the denominator cancel each other out, leaving behind the simplest of possible integrals, the integral of cos theta from theta 1 to theta 2. We integrate that, and we get the sine of theta. So sine theta 1 minus sine theta, sine theta 2 minus sine theta 1 is what's left. This is all in the z hat direction or the k hat direction. So here is our general expression for the magnetic field of a straight current carrying wire, where the theta angles are defined as shown in the sketch. Now, what would the special case be if the wire is infinite? Let's go back just a second to the picture. So if the wire is infinite, the left-hand end goes off to infinity, and so does the right-hand end, goes off to positive infinity. So the angle theta 1 would actually become negative. And if this left end goes as far away as possible, the angle theta 1 would become negative pi, or it would at least approach that in the limit. In much the same way, if the right-hand end goes off to positive infinity, then this angle theta 2 becomes closer and closer to, to pi over 2. Right, not to pi over 2. Because if this dotted line were horizontal, it would be pointing out toward a very, very distant end of the wire, then that angle theta would be pi over 2. So the limits for a infinite wire would be from negative pi over 2 to pi over 2. So we do that for this special case. Infinite wire, theta 2 goes to pi over 2, theta 1 goes to negative pi over 2. The sign of each of those guys, right, is easy to calculate. Sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. So 1 minus negative 1 is 2. And we get this rather simple answer. For an infinite wire, mu naught I over 2 pi r in the k hat direction. So we've actually gotten 3 simple results. We found, using Biot-Savart, the magnetic field at the center of a circular loop. We found it near a straight current carrying wire, a distance, perpendicular distance r away from the wire. And the special case of the second equation for an infinite wire is mu naught I over 2 pi r. And these are worth remembering. And so if we know these values, even without going back to the Biot-Savart law every time, we can often calculate the magnetic field of various kinds of current carrying wires. And you can think of many examples that combine circular loops and straight wire segments. For example, here's one. I won't do it, but I leave it to you as an exercise to the viewer. We have 2 long straight wire segments. Very, very long is what the dotted line indicates. So this wire comes in from the left from far, far away, carries a current I, and then it undergoes a quarter turn of a circular loop, and then proceeds on in the downward direction and goes way, way far away. So if this quarter turn of the wire is part of a circle of radius r, then what is the magnetic field at the center of the circular arc? And if you know the three results on this previous page, you can get the answer very simply. So we'll talk about that in class, and that's where I'll see you.